think we're good. Okay, hello everyone. My name is Tim Verbelen. I'm with Ghent University and IMEC, which is a research organization in Belgium. I'm basically doing research on AI and robotics basically. And with this talk, I was just going to go through some introductory material on what is this thing called deep learning, which is kind of hyping right now. Everybody it claims to use it. It's awesome. It solves all your problems basically. But what exactly is it? So maybe first off, a question: who is familiar with deep learning and is using it already? Okay, so perfect. So it's a very introductory talk. So if you would all already know about it, then it would be pretty useless. So let's kick off. What is this thing called deep learning? Well, basically, you can just say deep learning is just machine learning with neural networks, the same neural networks that they discovered like in the 80s and that are now kind of reviving. It's not something entirely new. They just found out if you throw lots more data and a lot more compute power at it, it seems to work even better, or it seems to work at least. So, what are the typical kinds of use cases where it has been proven to work? Well, we all probably know the kind of classic image classification, image segmentation task. So deep learning proves to be very good at analyzing images and telling you what's in the image or segmenting the image. It's also pretty good at speech and text. So basically, if you use Google Translate from time to time, it's now all operated using neural nets. Some more advanced stuff you can do is actually using the neural net to determine what action you should take. For example, in playing a game, you might have heard about Google's AlphaGo project, where they basically beat the best human AlphaGo player, which was never seen before for an AI. And you can also use it kind of to generate stuff. So, for example, if you have a neural net and you give it lots and lots of pictures of human faces, you end up with something that's actually able to generate a random face from a human for you. So it's basically analyzes the images, recognizes patterns from it, and is then able to use these patterns either to classify what's in it or either to generate new stuff that tends to look a bit like it. So, how does it work? Well, basically, they started this effort with how does the brain work and can we do something similar in software? So basically, if you go back to biology classes, you might know the brain is built up of several neurons, they call it, and they're basically cells in your brain, and what they do is they receive signal from any other neurons. So these are electrical pulses, and at a certain moment of time, if you have received enough electrical pulses, there's like a turnover point that this neuron says, okay, I received enough impulse, I will send an impulse to whatever comes next to me. And this is basically low level how your brain does stuff. And so they kind of try to translate this into software where we don't have this ability yet to do this continuous electrical pulse stuff. There are people working on it though, but what they do in software is basically they try to mimic this behavior by having the input being a number of floating point numbers. And inside your artificial neuron, you basically weigh each of these inputs with a weighting factor, you sum it up, and then you threshold it. And if it succeeds a certain threshold, then you forward stuff to the next neuron inside your graph. So that's basically how the tiniest building block of your neural nets, basically. So then what is a deep neural network? Well, it's basically stacking these things both in layers vertically as making them deeper by adding more layers to it. So this thing is then one layer in your neural net. It's basically one collection of these neurons. They're not connected amongst each other, but they're only connected to whatever comes before and whatever comes after it. And so then you can stack these layers, and the more of these layers you have, the deeper your neural net gets, hence the term deep learning. And these are often called the hidden layers. And so now, if we go back to the formula, you can basically treat all these neurons as a single vector, and your weighted sum becomes just a matrix multiplication. So you multiply your inputs from the previous layer with a weight matrix. You add a bias. The bias is basically to set the thresholding value of your thresholding function, and that's then the sigma, which can be any thresholding function. We'll look at it in more detail in a moment. So that's basically the building block of your neural net. And it allows you to, so under the hood is just multiplying matrices and doing some thresholding, and that's it. And that allows you to create any complex function, or at least to try to approximate any complex function using this building block. So I talked about activation functions. So what is it? So it's basically just kind of setting a threshold somewhere. So you might use, so the early neural nets often use a sigmoid, so it squashes everything between 0 and 1. So if you have a very low value, it becomes 0. If you have a very high value, it becomes 1. Something more popular nowadays is things like the rectified linear newt, where you just do it much simpler. You just say, if it's negative, I ignore it, I set to 0. If it's positive, I just push it through. They both have kind of their characteristics. I'm not going to go into too many details, but nowadays they often use the ReLU type things because it's easier to calculate, and it seems to work pretty good. So then we can kind of construct a neural network and see it as a flow graph. And this is basically if you try out any deep learning framework around, most of them will use the concept of a flow graph. Think about Google's TensorFlow, but also Torch, and Caffe, they all use kind of the concept of your neural net is built as a graph where you have your input, and then you, for example, you push your input through this linear layer where you do the matrix multiplication. It has this weights and a bias, and then you kind of do your activation function, and then you do a next one linear layer with some additional weights, and then you end up with your outputs. So here the output is a softmax. So basically what the softmax does is normalizing everything, so you can interpret it as a probability. So you use this, for example, for classification problems. What is the probability that in my picture I see a car, for example? So it kind of normalizes everything nicely. And that's then your function that is approximated by your neural net. And then the collection of all these weights and biases that you call the parameters. And by choosing these parameters wisely, you end up with a function that, for example, allows you to give an input as an image as an input, and outcome the probability that you see a car or a person or whatever. So the question is, how do you choose these parameters? Of course, that's the problem. So how do you train such a neural network? Well, basically you train it by giving lots of examples, saying, if you see this, then that's a car, and if you see this, that's a person. And by feeding it lots of examples, you can kind of tune the parameters in order to have something that works for your use case. So how does it work mathematically? So you basically treat your training as an optimization problem. You try to find in the space of all possible parameters, this one set of parameters that minimizes some function, which we call the loss. And the loss function is basically a distance metric that says, how close am I with what I really want it to be? And if you find amongst all the parameters the minimum, that gives you the minimum distance against all the examples I can give my neural net, then you basically have something that is able to classify new stuff. So for example, the distance metric in case of regression, this might just be the mean squared error. If you do classification, this might be the cross entropy loss. So for example, if you do classification, you just want to make sure that if it's a car, then my neural net should say, put the most probability on the thing being a car, basically. And how do we then get this optimum? And herefore we go back to our calculus class. So basically, if you have a function L and you have some parameters theta, in this case, it's a simple one-dimensional space. But we know that if we want to find the theta where we are at this point, we can take the first order derivative of our loss function through our theta, and then you just take steps downwards in order to get to this minimum. And if we are at the point where the gradient becomes 0, then we can know I'm in some local optimum at least, so probably we're good here. So the basic algorithm is that what you use to train your neural net is first you just randomly initialize your parameters. You take some of your training examples, images that are labeled, for example, you feed them through your neural net, you calculate the loss function, you calculate the gradient of the loss function, and then you update your parameters with a certain delta in the direction that you think is giving you a path towards this optimum. So then the last question is, how do we calculate this term, this gradient term? Well, again, from our calculus, we know that we can calculate the derivative of such a system using the chain rule. So basically, we had our flow graph here. What we do now is we have the output of our neural net and the expected output y that we want it to be. We calculate the loss function, so the distance that we're having, and then we can calculate the derivative of our loss function to the output, and then we can go each step back. So we can then calculate the derivative of the output to the softmax, and then we go back each step until we get to the very start. And then basically, if we would then want to know what is then the derivative of our loss function to the weights we actually want to choose, it's basically multiplying each of these intermediate parts together, and that's then your gradient, and then you can use to calculate the direction in which you want to update your parameters. And basically by feeding it lots and lots and lots of data, lots of examples, you basically go lower and lower and lower into your loss metric, and then hopefully you end up in a space where your neural net performs well and is able to classify an image as whatever you want it to be. So let's delve into an example. So for the examples, I'm using the DIANNE framework. It's basically something we developed at our university. So you can think of it as being a Java OSGi wrapper built around Torch. And it allows, we also created a web UI which allows to demonstrate how does a neural net works and to quickly prototype stuff and experiment with it. So it's basically because we have a visual aspect here that I'm choosing this one. You might use any other deep learning framework around to achieve similar stuff. And the first thing we will do is kind of the hello world example of deep learning. So that's the MNIST dataset. So it's a dataset of handwritten digits. So you get a 28 by 28 grayscale image which has a handwritten digit. And of course the question is, what digit are you seeing? So can you train a neural net to do this? So let's get started. So this is then basically our builder. So I will just build a very simple neural net. So we have our inputs and our outputs that just mark from here we start, here we end. And then we will use the linear layers. So these will do the matrix multiplication and adding the bias. And then we use, for example, the ReLU activation here. And we use a softmax. Actually, I'm using the log softmax here because it's numerically a bit more stable than using the softmax. That's just mathematical details, let's say. So we can connect our graph together like this. And now we still have to find out what are the parameters, how many weights do we want. So the input size was 28 by 28, which results in 784 pixel values that you basically have in your image. And let's be modest and just use a neural net with 100 so-called hidden neurons. And so then the next layer will receive those 100 values, and we output to 10 because we want to distinguish 10 classes. So here's our neural net. We can then deploy it on our runtime. Let's call it hello neural net. Here we go. So this is basically going from configuration to a deployment with OSGi services, just something internally for the framework. And then we can add our data set to the inputs and visualize the probabilities, basically. And you might see if we have a sample, then our neural net is not trained at all, so it just says, I have no clue what this is. I give probability to each one of the classes. So next step is to train our neural nets, and we have also a UI to do that. So this is basically kind of a job UI which we use to submit experiments, and then we can kind of keep track of how everything is doing. So in this case, we have our hello neural net. We want to use the MNIST dataset to train on. And then we have some additional options. So this is basically, if you will do deep learning, this is where the magic happens. So you have all kinds of hyperparameters that you can insert in any training procedure, and it's kind of just searching for the stuff that works best. So let me just have a basic overview of the ones I just pasted in here. So the criterion is basically our loss function. So we will use negative log likelihood, which is the basic loss function for classification problems. The batch size is 128, which means that we will use 128 images to calculate a gradient step, and then use this gradient to do a step, to update our weights in one step. Clean is true, which means I just want to initialize random weights. The tag is test, which means afterwards I can just recall the weights I trained with this tag. The trace interval is how often do I want to have a value plotted in the UI. And then I use a separate train set and validation set. So why do I do this? What happens with your neural net if you train too long on a certain data set, you will be basically overfitting to the data set. You just memorize each and every point you give it, but you will not be able to classify a new image that you've never seen before, because you're so focused on these are the examples I got, this is everything that's available in the world. If you see a new one, it might not work. So basically what you do is you take out a separate set where you don't train on, and you constantly evaluate your neural net on that set to see how good is it performing on data it never saw before. And once you see that it's actually becoming worse on that validation set, then it's a good time to stop training, because then you're kind of at your optimum. And I just set the maximum of iterations in order not to waste too much of your time. So let's submit it. And so now we can keep track of our job. So here you can see the training loss getting lower and lower. And every 1,000 iterations, I also evaluate on the validation set. So here you can actually see in real time the network gets better and better. Disclaimer, this is only happening on the MNIST dataset. If you do any real-world problem, it can take for weeks or months to get a graph like that. So, and you can also see that actually the performance on the validation set is kind of stagnating now. So it's probably a good time to stop already with this neural net training. So we're done. So if we go back now and we deploy the weights with our test tag, and we run a sample through the neural net again, hey, that's a 6. Another 6. Although it kind of puts a bit probability on a 5 as well, because it's not that clear. This is a 3, a 9, and so on. So you can see it actually learned how to recognize the patterns in the images. And you can also see that sometimes when it's not unclear, when it's a bit unclear, it also puts some additional weight on the other classes as well. So you can see which are the most probable ones according to the neural net. So that was our first neural network. Now, of course, if you treat your neural network as this, then you didn't have any assumption on what your input was. So basically, I had 28 by 28 images, and I just put an input of a flat vector of 784. And you might think, why do you do it? Because you know it's a square image, so you can use actually this information as well. And it turns out that in a lot of real-world data, there's a lot of structure in the data, and you know this up front, so why not exploit this? And especially for images, they started using the convolution layer. And this is one of the secrets why neural nets actually start working very well on these image recognition tasks. So basically what you do, instead of having a whole flat vector of all your pixels and pushing it through a neural net, you basically define this convolution filter. So for example, if your input image is 32 by 32, you have red, green, and blue channels, so 3 channels. Then you basically define a filter, for example, 5 by 5 with a depth 3, and you slide this filter over your image. So at each location of your image, you will multiply the weights with whatever is there in your image, and then you end up with one value. And if you then slide over this filter over your image, you end up with one new plane of 28 by 28, because you lose some information at the edges, unless you kind of pad it with zeros, for example, if you want to keep the spatial resolution. But the core thing here is that you use this filter that you slide over your image. And basically, if you think about it, it's quite sensible to do, because if you want if you want to recognize a car in your image, it shouldn't matter if the car is kind of shifted 3 pixels to the right, it should still be a car, right? So if you have this filter that shifts over and detects feature wherever in your image, if it detects a car, it should flag it and say, hey, I think it's a car. And then by defining multiple of these filters, you can transform any X by Y by Z image into any other new X, Y, and Z size. So it's especially the number of activation maps, they call it, will increase the more filters you use. And so now the key part here is if you calculate how many weights we have now is basically 5 by 5 by 3 plus 1 bias term, 6 times for 6 filters. So we have about 456 parameters we have to train. While if we want to go from 32 by 32 by 3 data points to 6 by 28 by 28 data points, and we want to do this with a matrix multiplication, you would end up with 14.5 million weights. So you can clearly see that we have a huge reduction in the number of weights we train, which speeds up everything and make it work actually for images. So as an example here, they have the IMAGENET dataset. So it's kind of a dataset with 14 million images that are labeled by humans. And it has thousands of classes ranging from all kinds of dog breeds to buses or planes or landscapes or whatever. So it has a wide range of classes. And it's kind of looked at the benchmark for image recognition technologies. So let's go to another example. So here we have a convolutional neural net for classifying images, and you can immediately see it's already quite a bit bigger than the simple thing we did first. And this one is already trained because I don't want to stuck you here for weeks. So if you give it a sample, you basically see this is the kind of image you get. So it's a mantis. And if you see, maybe, I don't know whether you can read it in the back, so the most likely classes the neural net says is grasshopper, I can't read it myself, cicada, or mantis. And so I wouldn't myself know the difference between a mantis and a grasshopper, so I think the neural net is doing pretty fine. So let us then check what is it that it learned? So what comes out of these convolutions? So we can also visualize that. So if you run another sample through it, then you can see that the first layer of your convolutions, so actually this one is a dung beetle, and the neural network says it's either a tiger beetle or a dung beetle, so it's pretty close. But if you look at what the convolutions learn, so the first layer is basically kind of extracting texture. You can see some of the filters, maybe it's not that visible in the back as well, but you have some filters that have like vertical textures or horizontal textures, other ones kind of segment background from foreground stuff. So you can see they have these low-level features that you as a human also would see in the image. They detect those. And if we go one layer later, let's say, and forward on our sample, you can see they actually combine this feature hierarchically. So the deeper you get to the neural net, the more you will have certain parts or certain filters being activated on certain textures in the image. And that's basically how it learns to classify all these images. Okay. So now what about memory? Because in often cases, your data has temporal or correlations. Also, for example, in text, if you want to process text, if you want to process a sentence, probably the meaning of the sentence also depends on the first word and not only on the word that you're looking at right now. So you need to find a way to kind of remember whatever you saw earlier. And a naive approach would be to just say, okay, whatever comes out of my neural net, I will feed it back at the first layer. So kind of have a kind of memory module that says that just remembers whatever you processed last time, and then you feed it back to the input. And this is a naive approach which works in some simple cases, but what you typically do is use a typically more complex memory cell. I'm not going to go into the details, but like an LSTM or a gated recurrent unit are most often used in these cases. And so as an example here, we will do something on characters. So basically, text you can see as predicting a character each time, depending on whatever you already saw before. So if I give you a sentence and I stop in the middle of the sentence, then often people will be able to predict whatever the next character is. For example, by looking at the word, it cuts in the middle. So this is kind of a typical benchmark problem to see, are we able to remember whatever we saw before and to condition our output on that. So basically what we will do, we will train a neural net that receives input from a character and then predicts whatever the next character will be. Then we feed that back to the input, and then we can just generate kind of text from it. And we train it using a data set of Shakespeare plays. So let's go to the final example. So here you can see these modules that I mentioned, which is an LSTM. If you want to see what's inside an LSTM, then it looks like this. It even doesn't fit the screen. So basically, without delving too much into the details, what you do is, this is the flow I mentioned. Whatever comes out, you feed back in with the memory block. But you also have an additional memory cell. And depending on what your input is, you will decide to kind of overwrite some parts of the memory cell, or to keep some of the memory cell, or to update parts of the memory cell, or to completely forget, reset stuff in there. So it's kind of a way to model with all the neural network blocks whatever you would think as a human that's useful for such a thing to remember. So if we go back to our neural net here, so then again we just stack one of those, and then we train it by feeding it lots and lots of data, characters coming from Shakespeare plays. And if you then see what it learns, so let's again do the deployment here. So what we will do now, we will feed it text at the input, but it will be the characters that the neural net itself generated. So we can choose how many characters we want to generate, let's say 1,000, and there it goes. And so you can clearly see it has learned the structure of a Shakespeare play. So it has a structure of, there is the name of a person, of a character, with a double locon, then there's an enter, and then it will kind of generate words that look like English. But if you read it, it's totally nonsense. It just kind of conditions how an English-looking word should look like. And so if I read it, so first Gregory says, "To my son, and then King Richard III says, "So France, she swear to their clients." And then the nurse says, "She's instrument, and tell me truly too." So it has no meaning at all, but you can see the word, it learns the words, it learns the structure of language. And so basically, it shows how such a thing is able to recognize patterns and then start generating these patterns over and over again for you. And if you do this on a kind of a word level instead of a character level, then you basically end up with models that currently are used by Google Translate to translate from one language to the other. So you input sentences from the one language, and you then have a neural net that generates the words for any other language, basically. And they train it using lots and lots and lots of example data. So let's go back to the slides. So this was basically it. So do not forget to evaluate the sessions and provide feedback. It's highly appreciated. If you have any more questions, I'm still around to answer them. If you're interested in the framework I showed, you can download it and look at the source code there. If you want to look at the examples I showed, they are also available in a separate GitHub, and there are lots more of examples. So more specialized topics on generation approaches and reinforcement learning and stuff. So if you're interested, take a look over there. And all I have to say is thank you all for being here and for attending. Yes?
Is there any way of specifying the deployment on several GPUs and this kind of stuff?
Yes, so basically every block you saw, you can allocate it on any device you have running in your system, basically. And it will also, depending on the device you're on, either use the GPU code or the CPU optimized code, depending on whatever is running there. Yeah. Yeah.
How long does that Shakespeare example take? Sorry.
It takes a few days on a single GPU. Let's say up to a week to get decent results. So, but it's also funny that you can, if you would look at intermediate checkouts of the weights, for example, you can see that in the beginning it's just completely random character generation, and then it starts to kind of do some enters to kind of have the structure of words in it, and then you can see it getting better and better in predicting so it first sees the high level thing, how does this stream look like, then it will start being better and better in the words, and even if you do it long enough, even the sentences might be more and more grammatically correct, and so it improves as you go. Yeah.
So are you training it, like, are you repeatedly passing in the same results?
Yes. Well, we have, it's I don't know exactly, it's a data set on a few of the plays, and you just randomly sample sentences from them, and you use those to train the neural net. Yeah.
But how does the heuristic look for that training?
How do you mean?
Like how does the AI evaluate if the sentence is good or not?
Okay, so basically you just evaluate. So the output is basically a probability for each possible character in your data set, and you basically train it to predict the correct one. Any other questions?
Is this kind of approaches, can they be used to, for instance, correlate a specific set of inputs to outputs? For instance, let's say that I have measures coming from sensors, pressures, temperatures, all these kind of things, and I have faults in specific cases. Is this approach good to detect and to correlate faults with the input parameters or perform these kind of things?
Yeah, so you can do such kind of things with neural nets. There are basically two approaches you can follow. One will be kind of the supervised type training you saw here, that basically comes down that you have a lot of data and you label it yourself. This is okay, this is false, and then you have to train it to detect the false ones from the good ones. Another way to do it is just give it good ones and then try to train it in such a way that it knows how good stuff looks, and if you see something entirely different, then flag it. This is something I never saw before, so maybe you should look into this. Yeah. So this is the way, but you can definitely use it for that as well. Okay, any other questions? Great, and you can all go for a good lunch.